Okay, this is an introduction to matrices for those that need to brush up. And this is the video for just the basics. And this is the topics that I'll be covering in this video. And hopefully I'll try to keep it as short as I can. We're going to do operations, adding and multiplying. We're going to find the inverse. We're going to do a little bit of elimination, find determinants, and solving some basic matrix equations. Okay, starting off, we have an m by n matrix, and that means you have m rows and n columns, and this is what it looks like. In the end, you can see we have m by n. So let's also talk about the entry, just so if we need to talk about position entries. It's ij, and that means the ith row and the jth column. A is n by n. And we can also have a column matrix. And our column matrix would be B, we usually do lowercase b n by 1, which looks like B11, B21, second row, one first column, and we go all the way down to B of n 1. So you see one column is called the column matrix. So to start off with our operations, when we're adding and subtracting matrices, it just requires the same size matrix. And just intuitively, you just add every single position. All the positions get added. That's why they need to have the same size. So multiplying, if I have a matrix A times a matrix B, I'm going to get a different matrix C. Let's talk about when can we multiply. Which matrices can we multiply? And if I have an m by n for A, and I have an n by p, little p, matrix for B, if these inside the inner are the same, they must be the same. Okay? If they're not the same, you can't multiply them. So if they are the same, then C will result in an m by p matrix. Okay? That's how that works. Now let me show you. Okay, there are actually many ways of multiplying, and I'm not going to explore all of them. But do know there is more than one way to multiply. Get the same answer. It's not like we get different answers. Just different ways of looking at it. So let's start off with 1, 2, 3. Let's make it not look like 23. 4, 5, 6. And we're going to multiply. So this is a 2 by 3. 2 by 3. 2 rows, 3 columns. So we need a 3, and we're going to do a 3 by 2, okay? The second one could be any size, so we're going to do 2, 1, minus 1, 2, 3, 0. And so what size matrix are we going to get? So these are the same, these are the same. So we are going to get a 2 by 2. Yes. So how do we do this? This is called the inner product. For this first position here, this first position, we're going to multiply. It's the dot product. You guys remember the dot product? It's the dot product. And so this is A1, 1. It's going to be the dot product of those positions. This one, column 1. Okay? So it's basically 1, 2, 3 times 2 minus 1, 3. And to do that, it's 1 times 2, 2, 3, 2 minus 1, 3. We multiply down, 2 minus 2, 9. So I'm just multiplying down. And that's I add them up. And I get 11, I get 9. So 9 goes there. Okay. So let's do, two easiest ones to know are this one here, position, just picking it randomly. I'm going to do the last two, that's 2, 2. Last, second. And so I can write it 4, 5, 6, 1, 2, 0, multiply down, 4, 10, 0, and I get 14. Okay? And then this one, this position here is a 1, 2, right? So for A1, 2, first row, because it's in the first row. I'll do orange. First row, second column. And let's do it here. 1, 2, 3. You can do this on scratch paper, and actually you can do a lot of these in your head. So I get 5. This last one, I'm just going to eyeball it. It's 8. 4 times 2 is 8. 5 minus 5 plus 18. I think we get 21. And there we go. There's our first multiplication. This is A, and this is B. Okay, what if I multiply? Let's try to do B times A. So I'm just flip-flopping those two. I'm going to have, and am I allowed to? So we got to be careful. 2 minus 1, 3. 1, 2, 0. That's my B. My A is 1, 2, 3, 4, 5, 6. And let's check it out to make sure before I go in, what kind of matrix, what size matrix am I going to get? So this is my 3 rows, 3 by 2 columns. This is my 2 rows, 3 columns. Let me put them next to each other. Okay, 2 rows, 3 columns. And we're allowed to because these inner ones are the same. So the out one, these have to be the same. And so we're going to get a 3 by 3. That's my answer, 3 by 3. Okay, 3 by 3. So let's do it. I don't know, maybe it goes a little faster because I think a lot of it you can do in the head. So this position, this is my A11. This is my A11. Not cooperating. So my A11 is going to be first row, first column, which is 2, 1, 1, 4. I add them up. 2 plus 4. I'm multiplying down, add them up. I get 6. And then my second one, this one is A12 is for the second one. So A12, first row, second column. And can we start doing these in our head? So 2, 1, 4 plus 5 is 9. My A13. I'm just moving down to the third one. 3 times 2, 2 times 3 is 6, plus 6 is 12. And you get faster at it the more you do. And so now we're moving to this position right here. So second row, we're on our second row. First column, minus 1 plus 8 is 7. And then I'm moving I'm moving over to the right. So those two I multiply and I get minus 2 plus 10, 8. I think that these are easier to do in my head than the last one. And I'm still here. Moving over to here though, looks like I get minus 3 plus minus 3 plus 12, 9. And then I'll keep that last one. We'll just move here. So this will be my last row, my last column. This gets this position here, right here. Okay, and so that's 9 plus 0 is 9. And then I'll move going kind of backwards here. 6 plus, that 0 is really easy. That's just 6. 6. And then my first one, I probably don't even need to highlight it for you guys anymore, do I? So that's just 3. Okay, you guys getting the hang of it? So what have we noticed? I mean, before we even started doing the B times A, clearly AB does not equal to BA. Okay, I've never seen that. Maybe on some square matrices, but not in any others. There's a new, this is my note. There's something called a transpose. And the transpose we signify with the power of t. So what a transpose does, for each ij, for each position, it just flip-flops the positions. Transpose, it turns it to ji, like so. Let me show you an example. So it flips everything though. So if I have A is 1, 3, 5, 0, minus 2, 1. So this is A. Then my transpose, my A transpose, it's going to flip-flop them. It's going to be a 3 by 2. Okay? So again, all we're going to do is basically this row is going to be this column. 1, 3, 5, 0, minus 2, 1. And let's just double check maybe one piece of it. So let's look at this. 5 is your A, 1, 3. That should move, that 5 should move to the A, 3, 1 position. And yes, that is your A, 1, 3. 3, 1. That is your A, 3, 1 position. So my example is 5t plus 3e to the t. Because of those pluses there, this is really a 3 by 1. This is my column vector, okay? Do you see that? This is one term. And so forth. So we're going to break it up. So we did 3 column vectors. What we want to do is we want to break it up as like so. 3 column vectors. And as far as like terms go, okay? So basically have my t's here, my e to the minus t's in this one, and my e to the t's here. So we can see we have my t's. I'm going to column exactly like this one, but this one is 5t0. Okay? My e to the t's, I don't have an e to the minus t in the second one, so we'll put it as 0. That's why this is a 0. There's a 0 plus. This is plus 0. If you want to look at it in three, there's 3 of them. So since there's t in this first one, I put a 0. And there's 2e to the minus 2 here, and then e to the minus t here. And how many e to the t's? Okay, maybe I want to highlight them. So this is there, right? So now if I go to my last one, I have 3e to the t, 0 of them there, 0 of them there too. So I write 3e to the t, 0, 0. And if we just double check again, we have 3 of the same size matrices. If we add them across 5t plus 0 plus 3t, that's what we get. Cool, right? Yeah. And if I add my second row, t, that's how they're all the same size. We just add those positions, the same positions counted. And my last one, 0 plus e to the minus t plus 0, which is a little bit easier to see here. I put the 0 placeholders in. Okay. All the t's, I pull the t out and I get 5, 1, 0. That's okay because that's kind of like a constant. Will get multiplied to each term in there. This is even the minus t. It's a common factor, not a constant. 0, 2, 1 plus e to the t. I can pull it out and get 3, 0, 0. So this coming up on the next video with eigenvectors. We find eigenvectors, that's what we'll be doing. So it's kind of an important concept. So the identity matrix is a square matrix, and for a 2 by 2 identity one, it's just 0, 1, 1. It's like if the identity for a 1 by 1, just a constant, is just 1. 1 times 5 is 5. That's what it does. When you multiply an identity matrix times another matrix, you get the matrix back. So that's a 2 by 2. And clearly we can have a identity matrix for a 3 by 3, which is 1, 1, 1, 0 everywhere else, and so forth. Now another concept that we're going to need is the inverse matrix. It doesn't exist all the time, only for some. It will sometimes exist, and it will sometimes only exist for square matrices for a n by n. Okay, so only square matrices have inverses, but not all square matrices. For some square matrices. Okay, if it's not square, you don't have you can't find an inverse. If it's square, we can find a way to figure out if it exists or not. We'll need the determinant, but I'll have to teach the determinant first. But finding inverses, we can find the inverses. If a equals 1, 2, 3, 5, what we can do, we'll have to use elimination to find it. 1, 0, 0, 1. There's several ways to find the inverse, but this is kind of just a row reduction method. And our goal, what we want to do is basically, so this is I. We want to convert it to I, A in this form. So we want to row reduce so that we have I in our front position and not our second position. Okay, that's our goal. So we do that by treating this as one matrix and row reducing it. So row reduction, I haven't actually done it yet. It's not very much different than if you're trying to solve two equations, two unknowns. You multiply both sides by 3, you subtract, the process of elimination for algebra, two equations, two unknown. It's the same thing. It's just a shortened way of writing it out. So I like to basically say what I'm doing though. So again, we want to work on the bottom row first. And so I want 0 right here. Okay. If I want 0 there, then I'm going to have to take minus 3 row 1 and then add it to row 2. And I still want to, I know it's getting small here. I also want to say, I'm going to put an arrow saying that's going to go to row 2, just so I know exactly what I've done algebraically. So my first row stays the same, 1, 2, 1, 0. And if you want to keep that in there, that's fine. You can drop it. So going to get a 0 there because it's minus 3 plus 3 is 0. Minus 3 times 2 is minus 6. Plus 5 is minus 1. And you have to continue it over here. Minus 3 times 1 plus 0 is minus 3. 1, 0, 0, 1. There's several ways to find the inverse, but this is kind of just a row reduction method. And our goal, what we want to do is basically, so this is I. We want to convert it to IA in this form. So we want to row reduce so that we have I in our front position and not our second position. Okay, that's our goal. So we do that by treating this as one matrix and row reducing it. So row reduction, I haven't actually done it yet. It's not very much different than if you're trying to solve two equations, two unknowns. You multiply both sides by 3, you subtract, the process of elimination for algebra, two equations, two unknown. It's the same thing. It's just a shortened way of writing it out. So I like to basically say what I'm doing though. So again, we want to work on the bottom row first. And so I want 0 right here. Okay. If I want 0 there, then I'm going to have to take minus 3 row 1 and then add it to row 2. And I still want to, I know it's getting small here. I also want to say, I'm going to put an arrow saying that's going to go to row 2, just so I know exactly what I've done algebraically. So my first row stays the same, 1, 2, 1, 0. And if you want to keep that in there, that's fine. You can drop it. So I'm going to get a 0 there because it's minus 3 plus 3 is 0. Minus 3 times 2 is minus 6. Plus 5 is minus 1. And you have to continue it over here. Minus 3 times 1 plus 0 is minus 3. And minus 3 times 0 is 0. I'm adding 1. I get 1. So if you ever forget what you're doing, it's listed there. And we're going to keep going with this. I'm going to scooch it over. Minus R2 changes it to R2 if you want to write it out. But basically, I'm multiplying both sides by negative is what I'm doing. So it's 1, 1, 2, 1, 0, 0, 1, 3, minus 1. Okay. Everything got switched by a negative. And I can go down this way if you like, or come starting on the left. It doesn't matter where you go. So this is going to be, now I want a 0 here, right? I want a 0 there. So it's going to be minus 2 plus 2 will give me 0. So how do I write that? Minus 2 row 2 plus row 1. And we're going to add that and replace it into row 1. If you do something like that too soon, you'll lose what you have. You just got to be careful on the order. I would just do one step at a time. That's the safest way. So here I get 0. So you notice how we've already zeroed that out, and now we're working on row 1. 0 times 0 times negative 2 is 0, and I add that, I keep that 1. I know I'm going to get a 0 there because that's how I set it up. And then minus 2 times 3 is minus 6. Plus 1 is minus 5. And minus this one here. Minus 2 times minus 1 is plus 2. Plus 0 is 2. And I just copy this bottom row. And I'm done. So what this tells me is my inverse is minus 5, 2, 3, minus 1. Okay, now this is a good exercise. I'm not going to do it, but we can check, what is an n? We can check by multiplying A inverse equals I, identity matrix. And it also has to be true for this way, because you don't usually get the same thing when you reverse the order. But in this case, since they are inverses, you can multiply them and see that you get the identity. Okay, it's actually very quick. So you guys, I really highly suggest you guys take the time to do that if you're a beginner here. So now the next question is, when does A inverse exist? So there's a major theorem here for this. The major theorem says if A is an n by n matrix, A inverse exists if the determinant of A does not equal to 0. If the determinant of A is equal to 0, then A is singular. It's called singular. So if the determinant of A does not equal to 0, then A is non-singular, and that means it's non-zero. That's how I remember it. We have a 2 by 2, A, B, C, D. So there's two things I should mention here about notation. So we can represent A like this, or we can go A, B, C, D. Okay, we can represent matrices with parentheses or square brackets, braces. But when we do determinant, now we can say the determinant of A looks like this. That's the notation for determinant, okay? And we can go A, B, C, D. I'm just saying there's a big string of equals. So the determinant looks like absolute value symbols. Okay, that's the notation that is the determinant. It's a single number usually, if we have just numbers inside here. But it's the formula. You kind of always start here, and you go multiply diagonal. AD minus BC. Okay? If you've had Calc 3, you've seen determinants. You've actually seen determinants of 3 by 3, but the problem is they may not have said it's the determinant. They may have not used that word. When you're finding the cross product, you're totally using determinants. Okay? And we can go A, B, C, D. I'm just saying there's a big string of equals. So the determinant looks like absolute value symbols. Okay, that's the notation that is the determinant. It's a single number usually, if we have just numbers inside here. But it's the formula. You kind of always start here, and you go multiply diagonal. AD minus BC. Okay, so now we're going to find the determinant of a 3 by 3. If you've taken Calc 3, you've already done this process before when you were doing cross products. It was actually the determinant. They may not have told you it was the determinant, but it was. So the way we do it is we're going to pick a row. I'm going to pick, for easiness, the top row. You can pick any row or any column, and I'll explain that a little bit more after I go through my first one. So I'm going to pick the top row. And to find the determinant of A, I can write the determinant of A, and that way I don't have to write out that whole matrix again. So the determinant of A, you're going to use the first position. A is positive, so it's A times, it's going to be times the determinant of a 2 by 2 matrix. The 2 by 2 matrix that we're going to find is what we're going to do is we're going to take A and we're going to cross off the row that A is in, and we're going to cross off the column that A is in. I know I'm highlighting it, but I'm really crossing it off. The 4 letters or numbers that are left are going to be your 2 by 2 matrix. It's going to be E, F, and we don't have to change any. We don't have to rearrange anything. Okay, so now my second one again, it's going to be B. Remember, we have a sign change for the second one. It's because the first position's plus. My second position always alternates, is negative, so that's a negative B, times a 2 by 2. The 2 by 2 will be, you have to cross off B, the row, and the column that B is in. The row and the column is crossed off. And so it's going to be times that those letters that are left, the numbers that are left, D, F, G, I. And then I'm going to my third plus C. Again, it's plus. It's alternating plus minus plus. So it's plus C times the 2 by 2. The 2 by 2 is, I highlight the row and the column that C is in. So my 2 by 2 is going to be D, E, G, H, just the ones that are left. actually is how you compute the determinant of a 3 by 3. If I feel like using a different row, again, let me write this out. We can use any column or any row. And the one we want to use is we want to use the one with the most zeros to make the computation go faster. The one with the most zeros. Again, I used row 1 here when I'm talking about, and that's this, this, and this. The letters that go in the front or numbers. I used row 1. And you can clearly see if B and C were both 0, well then this whole piece I wouldn't have to calculate because it would be 0 times that matrix, 0 times that matrix. I would just be A times that first 2 by 2, the determinant of that. So let's do it. Let's do one. Before we pick any row or any column, there's a little bit that we have to know. Notice how we had the sign change B. So it's not always plus minus plus if you, it just depends on what row or column. So what I'm going to do is I'm going to use, so plus, this is plus, it alternates everywhere. This is plus, this is minus, that's plus, and down it's minus plus. Alternates. That's a plus, that's a minus. So here's what the signs are. You always alternate. The first one is always positive. Okay, so let's say I would like to find, let's say I have the most zeros in this column. So using A above, I guess I could write it again. Using A, B, C, D, E, F, G, H, I. So using A, let's find the determinant of A. And we're going to use, obviously, this column. So the first of all, first B is in the negative position, isn't it? So it's going to be minus B times a 2 by 2. Which 2 by 2? The 2 by 2 that you obtain by crossing off the row and column of B. So it's times D, F, G, I. And then my second one that I'm going to use will be E, and that is a plus. So plus E times the 2 by 2. You cross that off. Oops. I cross off the row and the column that E is in, and I'm left with A, C, G, I. And last but not least will be a minus because it's in the minus position, H. So minus H times the 2 by 2. The 2 by 2. Again, I like to physically do it. You can probably do it by just looking. But that's what's great about this little device. So I cross off H, I cross off the row and column, and it's A, C, D, F. And there we go. So that's how we can find the determinant by 3 by 3. Now, the next thing that we're going to look at is the inverse, because the inverse of A is useful to solve. We have AX equals B. Okay? What I can do, you have to be careful. You can't left multiply over here and right multiply over here because it's not commutative. So we can left multiply by the inverse. So I'm going to, on the left, multiply by A inverse. On the right, I have B, but I have to left multiply by A. And so we can left multiply by the inverse of A. And what is A inverse of A times A? That turns out to be the identity. Times X is equal to A inverse of B. And when you have the identity times any matrix, you get that matrix back. It's just a column matrix equals A inverse B. And that's a way how to isolate X, which is our unknowns, and how to solve for X. We're going to solve, and it looks like we can just use Algebra 1 to solve this, 2 equations, 2 unknowns. But we're going to use matrices to solve this. And inverse. So first we need to write it in matrix form. And in the matrix form, it's going to be AX is equal to B. Okay. So X is our unknown, or X and Y is going to be a vector. X is going to be basically XY. You can choose X1, we can use X1, X2 as our unknowns if that bothers you, using X inside X, but it doesn't bother me. So sometimes it did at the beginning. But since we do have XY, so this is my B. My B is 7, 9. Okay. We have my X, which is XY. And my A, probably going to be 1, 2, 3, 5. But can we check this? If this is my first, we have a 2 by 2. Yeah. This is a 2 row by 1 column. And those are the same. And this is a 2 by 1. So therefore, it seems to work, but our first position, 7, first row, first column, only column, and we get 1x plus 2y, 1x plus 2y, and it does work. So 1x plus 2y equals 7. It works. And my second one, obviously, 3, 5, my 3, 5. If I multiply 3x plus 5y, then I get 9. So it works. So now we have our matrix AX equals B. And what I want to do is I want to find if my A is 1, 2, 3, 5. Do we have A inverse? I think that's the matrix we had up here. So let's go look. Yeah, 1, 2, 3, 5 was our A. And so I'm just going to cut and paste this. X is equal to A inverse B when I solved for it right here. Yeah. So A inverse. So my X is my XY. My A inverse is minus 5, 3, 2, minus 1, times my B is 7, 9. So if we write it out, again, this is my 2 by 2, my 2 by 1. Basically, I get my X equals minus 5 times 7 plus 2 times 9. That's my inner product of that times that. My first row, first column. And that's 35 plus 18, I think, minus 35 minus 17. And my Y, we'll do a different color here. Second row, first column. And that's 3 times 7 minus 1 times 9. There's the dot product of those two vectors. And that's 21 minus 9 is 12, I believe. Yeah, 12. So there's our answer. We have our answer for X. You can use algebra to solve that too. We got X equals minus 17. Y is equal to 12, but remember I said that's my X is my X vector XY, so X is also, meaning my vector X is minus 17, 12, and we can represent both answers either way. So we can use Cramers rule to solve. It's another solving technique, and if I know you guys have seen it before because it was on a previous exam. I'm going to solve the same equation using Cramers rule. So let me go find that equation. I don't need all of it. I just would like this matrix representation of my... So we're going to use the same equation to solve, to find X and Y. So if you remember, if I have AX equals B, this actually works for 3 by 3, 4 by 4, whatever you need. We are going to, the formula for Cramer's rule, it's x1, or you have x and y, equals a1 all over a, and x2, or my y, is a2 divided by a, sorry, the determinant of a. So it's the determinant of a1 divided by the determinant of a. But what is a1? So a1 is, it's the matrix. It's in general, when you have a, b, c, d times x, y equals a, b, c, d, we'll use e, f. So a1 is you replace the first column, ac, you replace this column with ef for a1. So it's ef b, d, that stays the same, the second column stays the same. The determinant of a2 is you just do it for the second row. So instead of putting EF in the first row for the first A1, for the second one, you replace, the first row stays the same, AC, the second row gets replaced with your B, which is your EF, and we know what A is. So that's how we do it. I mean, that's the formula for it. So let's do this one. A is equal to, and I need the determinant of A, so I'm just going to write that notation. The determinant of A, this is my A, right? So it's 1 times 5 minus 3 times 2, which is 5 minus 6, which is, the formula is A1, X is equal to A1 divided by A, the determinant of A. So A1 is divided by -1. We already found that to be -1. So A1, we replace 1, 3. I have it highlighted up here. Replace the first row with B, 7, 9. So it goes 7, 9 to 5. And the determinant of that, it's 7 times 5 is 35 minus 18, right? Which is still divided by -1. So it looks like it's 17 divided by -1, which is -17. Is that what we got last time? Yeah, it was. So that works. Let's do the second one. Y, or x2, call it whatever we want. I think I called it x2 up there, sorry. x2, that's x1, is A2 divided by A, that's the formula. A2, we'll just make the divided by -1, we found that. So A2, looking at our matrix, we're going to replace the second row because we're on the second one. The first row stays the same. Instead of 2, 5, it's 7, 9. And so that is 9 minus 21 divided by -1. That's -12 all over -1, which is 12. Okay, so I'm going to do it by, actually, you'll see what I'm going to do. In my notes, I have it done by elimination, inverses, and Cramers. Okay. I'm actually going to utilize some technology on this one. So the first, what we need is we need to write it as AX is equal to B. So to do that, we need our matrix where our B is clearly 8, 7, 4. Our X will be our X, Y, Z. And I have a 3 by 3 here. And that's just the numbers 1, minus 2, 3. 2, minus 1, minus 3, 1, 2, 2. So there it is. This is my A, this is my X, and that's my B. So since we just did Cramer's rule, I mean, that's probably what I would do on this one. Inverses for a 3 by 3, it's very tedious because you'll have to row reduce. And then we could also use elimination. That's usually the first thing you learn in a linear algebra class. So I'm not going to actually go through it in elimination. I'm going to show you my notes, though, where I did use elimination. And right here it is. So you can pause this video and work it out by elimination yourself if you want more practice. But here's the, this is called an augmented matrix. You have to, this is clearly my A. This is clearly my A. No, that doesn't work very good. This is my A, and this is my B. We kind of skip writing the unknown, okay? Because it's just X, Y, Z. We're trying to find X, Y, and Z. So in order to eliminate, we need to tag B along with our elimination. So we write, this is called our augmented matrix. Okay, so, and I do the little red line, you know, just like I did for when I was doing the inverses, it's augmented. So I'm just going to go through the first one for you. You always want to label what we're doing. So this first line says R1 plus R3, and we move it to R3. So I've highlighted R1, I've highlighted R3. We can see I add those two and I get 0. I add minus 2 and 1, and I get minus 1. And I add 3 plus 2. I mean, that one's just, it's just easy, just adding it. It's when you have to multiply it by. So the second one, you want to also be very careful in doing 2 steps in one. If they don't mess with each other, then it's okay. But it can make you get off a little bit if you do. So my second one, just 2 times row 1, I add it to, that the goal is to get a 0 here, because I already have a 0 there. So I thought it was safe to do those 2 steps, and so forth and so forth. And you can see I go across, I go down, I go left, and I go left. And if you want to see my augmented matrix, I'm going to rewrite it without it being augmented. And it's your identity matrix times your XYZ, your unknown, equals 5, 3, 3. Again, that's augmenting it. And I'm just picking on this last guy here. And so for this 3, it's this times this, last row times the first column. And clearly I get 0 times X plus 0 times Y plus 1 times Z equals 3. So I get Z equals 3. Okay, and so forth, and so forth. Okay, so let's go back. So that's how you do it for using the elimination method. So let me just write down the answers that we got, by the way, if I'm going too fast. We got Z is equal to 3. Y is equal to 3, X is equal to 5. X is, you have to do it in order, 5, 3, 3. Okay, so that's what we got as our solution. And now inverses. So for inverses, again, it's so simple. If you forget what the formula is, you don't have a formula to memorize. You see we have AX equals B. We have that. I left multiply by A inverse, and then I get X by it, that cancels because that's I, equals A inverse B. So there's our formula. So all we have to do, such a simple little thing, is to find A inverse. So in order to do that, I mean, we know how. I showed you a method how to do it by hand, but let's be real. We're not always going to do things by hand. So what I'm going to do to find the matrix, to find inverse, you can, if you have a, TI-83 or something, you have the technology on your graphing calculators, and even some of the smaller cheap calculators, you have the ability to find inverses. And so I'm just going to show you online. You can actually find it, use it on your phone. I'm going to do it on this tablet, but we're going to do online search to find it. I mean, Wolf and Alpha does it, but it's actually harder and takes longer to do it on Wolf and Alpha. But I'm going to search for matrix calculator. Okay. And you do that search. And I already did that search on here. And this is the first thing that comes up, matrixcalc.org, if you want to see it. matrixcalc.org. And so I've actually put the first two lines of that A in there, because I want to show you how to use this. So this third line, we need a -1, so you use that -1, and then a 1, and then a 2. So it's really easy to type in the matrix. And so now we want the inverse, correct? And remember, it's just A inverse times B. And so A inverse, go ahead, find the inverse. And let's go a little smaller. And I know it's hard to see, but you need to see if I make it too big, it cuts off the stuff that I need on the right. So this is my inverse. It says, here's the notation, this inverse equals -875. Now, you can write that down and go up there and type it in again, but this is really neat. That's what I really like about this. I want matrix A. Again, left and right makes it different. I want matrix A up here to be A inverse. Okay, and B, I'm going to input B, little b, and I'm going to multiply them. See how in the middle we have A times B, A plus B, or A minus B? I'm going to hit multiply them. So I'm going to insert this answer, my inverse, I'm going to insert it in A, okay? And see how it changed? Matrix A is now my A inverse. You just got to keep that you got to keep track of it. And so in B, matrix B, I'm going to put in my lowercase b, which was 874. I see there's if I go smaller, it makes a 2 by 2. I need a 3 by 1. So really all you need to do is just do the first column and it'll work. So I'm going to type in 8. This is my B, 7, and 4. Okay. And you can leave it blank. If you put zeros in, then your answer will be a 3 by 3. This is a 3 by 3 times a 3 by 1. You'll get a 3 by 1. Okay. If you put zeros in, that's fine too. You can fill it in by zeros. Then you're multiplying a 3 by 3 times a 3 by 3, and you'll get a 3 by 3, but you'll have zeros on the 2 right-hand columns. Okay. So I'm going to just keep it the way it is so you can see. And then I'm going to hit up here, A times B. And look at that. There's our answer, 533. Remember, that's an easy answer to remember. So it's showing you this. I wish I could write on here. I can't, but it's A inverse times my little b, and I got the same solution as I did by elimination. And that's pretty cool, huh? So let's go back. I'll write it down in here. So my A inverse, I found out to be -875 -654 -1 1 1, and we found out when I multiplied, x is A inverse times b, so it's -875. I'm just copying this again, sorry. Times -1 1 1, and I times this by little b. Right? That's what we're doing right here. Little b was 874. How do we know that? Because there's my A, there's my B, little b, 874. And we get 5 3, 3. And you can just sit there and multiply that on your own too. We want to just double check the middle one. I want to double check this. So this is the second times that. And we can see it's minus 6 times 8 times plus 5 times 7 plus 4 times 4. Okay, so dot producting them. Minus 48 plus 35 plus 16. Use a calculator or do it in your head. Keep going and you get 3. So that's neat. You can, multiply all 3 of them if you wanted to, but I did it on the calculator. And last but not least, again, we can use Cramers. Cramers, I'm not going to actually do this one, but we can do it using the graphing, the technology that we just pulled up. We get x1 equals a1, the determinant of a1 divided by a. And we get x2 equals a2, the determinant of a2 divided by determinant of a. And x3 is equal to the determinant of a3 divided by the determinant of a. And if we want, we can go back and use that. Well, what's going to happen if I inverse this? Because it's the same problem, wasn't it? Find the inverse. So there's my a again, because I took the inverse of the inverse. Was that a big surprise? So if I want to put that back in a, I insert an a. And I want to find the determinant. I just have to find the determinant. And we get 1 there. Okay, so we get a determinant of a, you should write that down, is 1. Or you can go online and pause and go do this all yourself. And then you can replace this first column up here with 874, might be 8, 7, 4. And then what do? We got to find the determinant. And I get 5. So my answer is 5 divided by 1. And I'll go back there and write it. So this is going to be the determinant of 8, 7, 4. And we got to fill it in. I've lost it. So we have 8, 7, 4. And then I just changed the first column, right? And I keep the other 2 columns. Minus 2, minus 3, 1, 3, 2, 2. And then we know that's divided by 1. And we get 5. And then my second one, I'm going to keep 3, 2, 2. I'm going to put 8, 7, 4 here. And this one is 1, 2, 1. And I'm going to get 3 for that when you throw it in to that determinant. And for this last one, it's 1, 2, 1, minus 2, minus 3, 1. And I replace this last column here with B, 8, 7, 4. And I get 3 again. And because that's divided by 1, which is kind of nice to get that divided by 1. Okay, that's it. Thank you very much.